Think about pushing a block across a table. It moves in a simple straight line. Now look at a structure like a massive Ferris wheel. You cannot push it linearly. It is pinned to a central pivot, forcing every piece of steel and glass to move in a strict circle. If you apply force directly dead center into that pivot, nothing happens. The wheel will not budge. But shift that force to the outer edge, pushing tangentially, and the entire structure begins to turn. To understand exactly how this works, we have to zoom in and isolate a single microscopic particle on that wheel, sitting at a specific distance or radius from the central axis. When a perpendicular force strikes this specific point, it pushes the particle along a curved path. It is experiencing a linear push, but because it is tethered to the center, its resulting movement is entirely circular. In straight line motion, a direct push causes linear acceleration. But when an object is locked to an axis, that push becomes a twist. We call this twisting equivalent torque, and it is the precise physical mechanism that commands a rigid body to spin. We do not need to invent new physics to calculate how objects rotate. We simply need a translation guide to adapt Newton's classical rules of linear motion into the language of spinning bodies. Let's start with the baseline metrics. On the left, an object moves a measurable distance in a straight line, which we call linear displacement, denoted by the letter x. On the right, our rotating object turns through a specific angle. This is angular displacement, represented by the Greek letter theta. As both objects move faster, the sliding block gains linear velocity, v. The wheel, meanwhile, sweeps through its angles faster, giving it angular velocity, or omega. Angular velocity is the rate at which an object rotates around a fixed axis, measured in angles per unit of time. Faster, more energetic. If they continue speeding up, they are accelerating. Linear acceleration, a, translates directly to angular acceleration, alpha, the rate at which the angular velocity changes over time. This perfect mapping means every linear equation provides a direct blueprint for its rotational twin, allowing us to describe the movement of spinning objects with absolute precision. Newton's second law dictates that force equals mass times acceleration. If that is the supreme rule of the linear world, what is the master equation for rotation? We start by looking at mechanical work. In a straight line, work is calculated by multiplying the force applied by the total distance the object moved. If we use our translation guide, force becomes torque, and linear distance becomes angular displacement. Rotational work is simply the torque multiplied by the angle the object turns through. Mechanical power, the speed at which that work is done, undergoes the exact same shift. It changes from force times linear velocity into torque times angular velocity. By taking that rate of work and setting it equal to the rate at which the rotating object gains kinetic energy, we can calculate exactly how much it will accelerate. The math simplifies down to one elegant line. Torque equals I times alpha. That I stands for moment of inertia, the rotational analogous of mass. Moment of inertia is a numerical measure of a body's resistance to rotational acceleration. This formula is the definitive rule governing how a rigid body spins when a twisting force is applied. Let's test this equation with a theoretical experiment comparing two shapes that weigh exactly the same. We have a solid disk and a hollow ring with its material pushed to the edge. A scale confirms identical masses. Applying the same torque, the solid disk rapidly spins up, while the hollow ring accelerates sluggishly, lagging behind. Because the mass of the hollow ring is located much further from the central pivot point, it possesses a naturally higher moment of inertia. It simply has more resistance to being spun. Total weight does not dictate how hard something is to rotate. The physical distribution of that mass is the absolute deciding factor in how an object responds to torque. This principle is essential to the heavy machinery that powers the modern world. Early steam engines and modern car engines share a mechanical challenge. They do not produce power in a smooth, continuous flow. They generate energy in violent, jerky bursts, with dead zones in between. Engineers solved this by attaching a flywheel, like the massive, heavy-rimmed green disc you see here on this steam engine. This component is designed specifically to exploit moment of inertia. Because its heavy rim concentrates the weight far from the central axis, the flywheel strongly resists changes in speed. It absorbs those violent bursts of engine torque and uses its momentum to power right through the dead zones, keeping the engine turning at a steady rate. Rotational dynamics provides more than just a theoretical mirror of linear physics. It is the fundamental mathematical bedrock that allows us to build machines that turn smoothly and safely.